All right. Well, thank you for coming and listening to my lecture about radiation. My name is Dr. Aaron Frey. I'm one of the medical toxicology fellows, as well as an emergency medicine physician at the University of Virginia, as well as the Blue Ridge Poison Center. And like I said, today we'll be talking about radiation and its associated medical effects. Now, our objectives for this lecture will be able to define radiation, where we'll understand the difference between non-ionizing and ionizing radiation. We will give examples of the different types of ionizing radiation and have a basic understanding of them. We will understand the concept of low energy transfer, or LET. We will understand ALARA principles. We will understand acute radiation syndrome, and we will describe the medical treatment for acute radiation syndrome. So let's first start with the question, what is radiation? Well, radiation is energy that is propagated through space. It has properties of both a wave and a particle. Electromagnetic radiation is a spectrum of wavelengths and corresponding energy. On this spectrum are waves with large wavelengths, such as radio waves, and have low energy and are not harmful to humans. On the other end of the spectrum are gamma rays, which have small wavelengths, high energy, and are harmful to humans. Also in the electromagnetic spectrum is visible light, which is the only part of the electromagnetic spectrum that we have the ability to detect with our senses. Radiation that has shorter wavelengths has more energy, and those that have more energy have more of an ability to cause biologic damage. Humans experience deleterious effects when exposed to ultraviolet, X-ray, and gamma ray radiation. These higher energy waves cause damage by their ability to alter the atomic structure of the matter they interact with. They have sufficient energy to eject an electron from an orbital shell of a target atom. This ejection creates charged particles or ions, and if certain biological molecules become ionized, it can eventually cause cellular death. The radiation capable of doing this is called ionizing radiation. Ionizing radiation is emitted from a radioactive source. It can be in the form of a particle, such as alpha radiation, beta radiation, or neutron particle emission, or it can be in the form of waves, such as X-rays or gamma rays. So, where are the sources of ionizing radiation? Well, there are natural sources, such as cosmic radiation and terrestrial radiation. And then there are man-made sources, such as nuclear power plants, medical devices, equipment, and therapeutics, and then also nuclear weapons. All of these things possess the same thing: unstable atoms, which are called radioactive isotopes. So to understand isotopes, we must understand some foundational concepts of atomic and nuclear physics. The basic building block of all matter is the atom. The atom consists of a central nucleus surrounded by a shell of orbiting electrons. The electrons have a negative charge. The nucleus has two parts: neutrons, which lack a charge and is therefore neutral, and protons, which are positively charged. The strong nuclear force is what holds the protons and neutrons together in the nucleus. At very small distances, the strong nuclear force overcomes the electromagnetic force repelling the protons and neutrons from each other. Each element is defined by the number of protons in its nucleus. The number of protons in an element's nucleus is called its atomic number. In this cartoon, we see the carbon atom, which is identified by having 6 protons in the nucleus. For a stable nucleus, the usual ratio of protons to neutrons is 1 to approximately 1.2. However, there can be varying numbers of neutrons in the nucleus of an atom. Those with different numbers of neutrons are called isotopes. In this example, we have a carbon atom with 6 neutrons, so the total number of protons and neutrons in the nucleus is 12. This number is the atomic mass number. When we discuss this isotope, we call it carbon-12. It is the most common isotope of carbon. When written, the atomic number is written as a subscript to the left of the element symbol. The atomic mass number is written as a superscript to the left of the element. Isotopes can be stable or unstable. Unstable isotopes can be radioactive and give off energy in order to become stable. They are also called radioisotopes. Such radioisotopes may undergo decay by emission of energetic quanta. In this cartoon, we have two different isotopes of uranium, uranium-238 and uranium-235. Both are radioactive isotopes. Both have 92 protons, but uranium-238 has 146 neutrons, and uranium-235 has 143 neutrons. Now, we discussed all of that to go back to the original topic of the different types of ionizing radiation. An unstable radioactive isotope can become stable by altering its components in the following ways. It can emit an alpha particle, which consists of 2 protons and 2 neutrons. It can emit a beta particle in the form of an electron or a positron. Now, a neutron can change itself into a proton by the emission of a negatively charged beta particle, or an electron. So, the neutron becomes a proton plus an electron. A proton can change itself into a neutron with the emission of a positively charged beta particle, also known as a positron. So, a proton becomes a neutron plus a positron. There also can be the emission of neutrons from the nucleus of the atom. There can be emission of X-rays, and there can be an emission of gamma rays as well. X-rays are emitted when an electron moves from a higher orbital to a lower orbital. And when particles have been ejected from the nucleus, there can be an excess of the strong nuclear force which has mass. This excess mass is removed from the nucleus by being converted into energy. And this is where the famous E equals mc squared formula comes into play. Now, the mass gets converted into energy, specifically short wavelength, very high energy gamma rays. This emission of gamma rays, derived from the strong nuclear force, is what results in the formation of a stable nucleus. Now, it is important to realize that an unstable radioactive nucleus can interchange its components to achieve the ratio of 1 proton to 1.2 neutrons. If the number of protons changes, then a completely different element is formed. This can occur with those radioisotopes that emit alpha or beta radiation. So now I'm sure some of you are probably relating to this meme. So let's look at some illustrations to visualize these concepts. So in this cartoon, we have the unstable radioisotope uranium-238, labeled as the parent nucleus in this cartoon. And it is emitting an alpha particle to become more stable. It emits the alpha particle, which remember consists of 2 protons and 2 neutrons, which also happens to be the nucleus of a helium atom. Because remember that an element that has 2 protons in its nucleus is helium. Since the uranium-238 emits 2 protons and 2 neutrons, it has become an element with 90 protons, which is known as thorium. Since uranium-238 emitted 2 neutrons and 2 protons, the total amount of particles lost from the nucleus is 4. When we subtract 4 from 238, we get 234. This is why when uranium-238 emits an alpha particle, the resulting atom is thorium-234. The thorium-234 nucleus is still unstable after the alpha emission, and so it emits a gamma ray to help de-excite itself. In this cartoon, we have thorium-234 emitting a beta particle in the form of an electron to become stable. Remember that in the nucleus, a neutron can change itself into a proton and an electron in order to release energy to become more stable. So in this example, thorium-90 changes one of its neutrons into a proton and an electron. The resulting nucleus now has 91 protons. An atom with 91 protons in its nucleus is protactinium. The total number of particles in the nucleus did not change, so the new isotope is protactinium-234. Again, in this example, the resulting new atom has an excited nucleus, so it emits a gamma ray to become more stable. This cartoon illustrates the emission of a beta particle, but in the form of a positron. A positron is like an electron, but it has a positive charge. Remember that an unstable atom can change a proton into a neutron and a positron. The resulting atom will have 1 less proton, so it will become a different element. However, the number of particles in the nucleus did not change, so it will have the same atomic mass number. The emitted positron will combine with an electron in another atom, annihilating each other, which results in the release of two photons released at 180 degrees from each other. X-rays are a type of electromagnetic radiation that have properties of a wave. They do not have mass and do not behave as particles. They are emitted when electrons in an orbital shell drop to a shell of lower energy. Gamma rays also behave like waves and not like particles. When a nucleus is in an excited state, it is said to be metastable. It is sometimes abbreviated with a lowercase m beside the atomic mass number, as illustrated in this example. The nucleus releases gamma radiation to become more stable. Since no particles were emitted from the nucleus, the number of protons and neutrons does not change. So the daughter element has the same atomic number and atomic mass number, as illustrated in this cartoon. So now that we have covered the different types of ionizing radiation, it's important to understand something called linear energy transfer, otherwise known as LET. Linear energy transfer describes the ability of a particular radiation to deposit its energy along its path as it moves through another material. It is the average energy deposited per unit path length. It is an important concept because chemical and biological effects are directly linked to the magnitude of ionization in the tissue. In many materials, the energy required to produce an ion pair, and remember the ion pair is going to be the removed electron and any remaining positively charged particles, is estimated to be between 30 and 40 electron volts. Now this energy is more than enough to break a double bond linking one carbon atom to another, as found abundantly in the base pairs of DNA. Alpha particles and neutrons are very efficient at this. They are called high LET radiation. They are very good at causing biologic damage. Beta particles and gamma rays and X-rays are relatively inefficient at causing ionizations and are referred to as low LET radiation. So it's important to remember that biological damage produced by radiation increases as the LET of radiation increases. So again, this is a key concept to remember. Equal doses of different types of radiation do not produce equal biological effects. 1 gray of neutrons produces a greater biological effect than 1 gray of X-rays. And we're going to discuss what a gray is momentarily. So now that we know what ionizing radiation is and how it can deposit energy into tissue, we need to discuss the concept of shielding. Alpha particles are relatively large when compared to the other types of ionizing radiation and are very interactive with other matter, and they lose energy very quickly. They have a very high ionizing power. Their LET radiation is very high, but they can travel only a few centimeters in air, and they can be shielded with one sheet of paper. Beta particles are less ionizing than alpha particles. They can travel farther than alpha particles, about a few meters in the air, and they can be shielded by using plastic, glass, or thin layer of metal. Photons such as gamma rays or X-rays are even less inefficient at ionizing. They can travel many meters in air, and they likely interact in the ion cloud of an atom. Heavy, dense materials, ones with high atomic numbers, such as lead, are effective shields because the higher number of protons in the nucleus results in a larger number of electrons circling it, which would increase the probability that the photon would be able to interact with electrons. So how can we use the concept of shielding to help devise a plan to protect ourselves from ionizing radiation? Radiation protection follows the principle of ALARA, which is keeping exposures as low as reasonably achievable, which is achieved by both time, distance, and shielding. Radiation follows the inverse square law. Intensity of the radiation dose decreases inversely with the square of the distance. So the further you are from the source of radiation, the less amount of radiation that you will be exposed to. Placing appropriate shielding between you and the radioactive source will also decrease the amount of radiation that you may be exposed to, and that's something we have just discussed. And we can also minimize the time that we are in the presence of a radioactive source in order to minimize the amount of radiation that we are exposed to. So in summary, we have alpha particles, which have very low penetrating power, but they are able to ionize very efficiently. So they're very dangerous if they are incorporated into the body through inhalation or ingestion. However, if you were to encounter an alpha emitting source, your outside skin layers will be able to protect you from it. It wouldn't be able to penetrate. Beta particles are smaller than the alpha particles, so they can travel further. They can penetrate a little bit deeper than alpha particles, but they're not as ionizing as the alpha particles. So it takes something a little bit more dense and something a little bit more thick in order to shield yourself from them, so something like aluminum. And then you also have gamma rays and also X-rays, which act as waves. They don't act as particles. They can penetrate very deeply, but they do not ionize very well. And it takes something that's very thick and something very dense, such as lead or other elements, to protect yourself from them. So I'm sure many of you are related to this cat. Please, no more physics. It hurts. And I hope you understood the hertz, dealing with the wavelength there, a little pun on words. And also remember that many people think that the F in physics stands for fun. And notice there's no F in the word physics because many people do not think there is any fun in it. So we're going to be kind of moving from the concepts of atomic and nuclear physics to talk about something a little bit more related to the biological effects, which many of us are interested in. And we can start that with the discussion of irradiation versus contamination. Now, irradiation deals with being in the presence of ionizing radiation. There's no transfer of radioactive materials required for this to occur. One that's been irradiated cannot contaminate others, equipment, or facilities. And it's important to remember that being irradiated only occurs when people are exposed to ionizing radiation, much in the same way that a person is exposed to light when someone shines a flashlight on them. They're not going to be emitting light just because they've been exposed to it. Now, contamination is a different concept. Being contaminated is when people or things have radioactive materials either on them or in them. Or in other words, when radioactive materials are transferred to another surface. Now, things that are contaminated can either be externally contaminated, such as when you get radioactive materials on the outside layer of your skin, or they can be internally contaminated. And that can happen through inhalation, ingestion. It can happen if you have a wound on your skin and it gets exposed to radioactive materials. And it also can happen if something that has radioactive materials on it and penetrates your skin. So think of something like a dirty bomb that has radioactive materials on it, and you get hit by a piece of shrapnel that has the radioactive material on it. So now we'll take a look at how ionizing radiation damages the body. The danger with ionizing radiation resides with its direct and indirect effects. Direct ionization effects occur when a radiation directly strikes a DNA sequence, causing a break in the strand. If the damage cannot be repaired, then the cell can die. Indirect damage occurs when X-rays or gamma rays strike a molecule of water and generate a free radical. These free radicals can then cause damage to the DNA, which can result in cell death. Now, when we talk about the biological effects of ionizing radiation, the terms deterministic and stochastic are often used. Deterministic effects are those biological effects that occur early in the exposure to ionization. The radiation dose essentially determines the effect, hence the name deterministic. Certain biological damage only occurs when a certain dose threshold is met. Examples of this would be acute radiation syndrome and its subsyndromes. It is illustrated in this cartoon on the left-hand side of the screen. Stochastic effects are essentially those effects that occur by chance. An example of this is carcinogenesis. It occurs randomly and independently, and the probability of health effect occurring is proportional to the dose. It is illustrated on the right-hand side of this cartoon. Now, an important concept to understand when it comes to the biological effects of ionizing radiation is the concept of radiosensitivity. Not all human cells are affected by radiation to the same degree. The concept of radiosensitivity was described by the law of Bergoni and Tribundow in 1906. It states that cells that are actively dividing, which is to say that they are mitotically active or have a high mitotic index, and cells that are immature or not well differentiated are much more radiosensitive than other cells. Following this law, the relative sensitivity of hematopoietic progenitor cells, epidermal stem cells, gastrointestinal stem cells, such as found in the crypt cells of the GI tract, and endothelial cells are more susceptible to injury from ionizing radiation. The manifestation of damage to these cells is what defines the subsyndromes in acute radiation syndrome. Now, there is an important exception to this rule. Agranulocytes, particularly lymphocytes, are exquisitely radiosensitive, but they do not undergo mitosis at all and are thus terminally differentiated. This concept is extremely important to know. White blood cell differentials and radiation injuries will show a dose-response decrease in the absolute lymphocyte count. So if you were to measure a complete blood cell count over time and comparing that measurement with a previously established curve, you can have a prediction of what the dose of radiation that person was exposed to. Those that have a fast, large decrease in lymphocyte count have been exposed to a larger amount of radiation. This can be used to help guide prognostication and the allocation of resources that the individual may need, especially in an event such as a mass casualty incident where resources are low. Now, this graph illustrates the concept using the lymphocyte count as a dose estimator of radiation, and you can see with this that the absolute lymphocyte count 48 hours after an exposure is a good predictor of how much the hematopoietic system is involved. At 48 hours after exposure, if the absolute lymphocyte count is greater than 1,200 cells per microliter, it is unlikely that the patient has received a clinically significant dose of radiation. However, if the absolute lymphocyte count falls between 100 and 500 cells per microliter at 48 hours, then a significant or even lethal dose of radiation should be suspected. Now, this is not a 100% steadfast rule, but it is a good way that we can estimate how much radiation one has been exposed to. So now that we have covered the basics of ionizing radiation and the concept of radiosensitivity, it is important to discuss a few terms and units of measurement of radiation before we talk about how different radiation doses can produce certain effects. Radioactivity is measured by its decay rate, or in other words, how many disintegration of an atom per second. One disintegration equals 1 becquerel in the international system. In the United States, activity has been measured in units called curies. 1 curie equals 3.7 times 10 to the 10th decays per second. Radiation dose is the amount of radiation deposited into the human body. In the United States, it has been measured in rads. The SI unit is gray. 1 gray equals 100 rads. Each type of radiation has different biological effects on the tissue. The equivalent dose is a measure of the radiation dose to tissue that equates the biologic effect from various forms of ionizing radiation. It is calculated by multiplying the absorbed dose by the radiation weighting factor, otherwise known as the WR. This factor is dependent on the type of and energy of the incident radiation. The value of WR is 1 for X-rays and gamma rays and beta particles, but higher for protons and neutrons, and alpha particles and heavy fragments have the highest weighting factor, around 20. Now, the LD5060 is the dose of ionizing radiation that would kill 50% of a group receiving that dose within 60 days without medical treatment. And that dose actually equals approximately 400 rads, or 4 gray. Now, the half-life is the amount of time it takes for the activity to decrease to half of its original amount. So that will finish this section of radiation, dealing with the basic concepts as well as the atomic nuclear physics review. And I hope to see you on the next iterations of this lecture when we talk about the biological effects, and as well as going over some case reports. So thank you.